So we'll continue from last week. The textbook and this is a different book. We will this week. We can process and this is a application. We will continue video for design for single continuous learning respected to learn and regional research. So continue with so last week we was about targeting minimum wastewater treatment for single container we stop example 26.3. The example is regarding table possible for this we use table 26.9. So one complication not considered so far that is very commonly encountered in effluent system is some of the effluent are already below their environmental discharge limit. For last example, example 26.3, all the stream has concentration more than the environmental discharge limit of 20 ppm. So this example is for what happened for less than 20 ppm. So stream 4 is less than the discharge limit. This table is different from table 26.8. So for stream 3, 30, the flow rate of 20, stream 4 is 10 ppm only, with a flow rate of 50 ton per hour. Note from table 26.9, the extreme 4 with a concentration of 10 ppm is below 20 ppm. Suppose that this to be treated with operation capable of producing 5 ppm blood concentration. So how can we target minimum flow rate be set under such circumstances? This topic is continuity from subtopics targeting minimum wastewater treatment flow rate for single contaminant. In fact, the validity of the stream with concentration below the environmental limit remove parts of the environmental load to be taken up by the effluent treatment system through with dilution effect. The construction of the effluent composite to include this effect is shown in figure 56.51. The environmental limit is 20 ppm. However, for stream 4, the C in concentration only is 10 ppm. The discharge should be 20 ppm, still the same, with 80 ton per hour of flow rate. So negative 0.8 here. So MC here refer to kilogram per hour. MC how to calculate it is 80 divided by 10 ppm. 10 ppm. Times 1000. Normally MC is MC in kilogram per hour. So no need to multiply with 1000. Can we see that the stream starting at 10 ppm increases in concentration to the specified method of limit of 20 ppm? It takes a part of the effluent load from the other stream that would otherwise have to be removed by the effluent treatment process. The dilution effect of the stream below the environmental limit effectively create a new environmental limit with the 20 ppm. The target for the problem is shown in figure 26.43. For this figure, the composite curve figure, unity composite curve, is constructed based on table 26.9 with the water supply line pitch at 52.6 ton per minimum flow rate is 52.6 ton per hour. So here we have 10 to 20. The water supply line is up, stop at 5 ppm because they mentioned this operation capable of producing outlet concentration of 5 ppm. In this case, the specification for the treatment process was based on an upload concentration. If the specification had been based on the removal of social, you still remember last example, So for targeting the minimum wastewater treatment for single contaminant, you have two methods. The fixed outlet concentration or the you specify the removal ratio. That one you can refer to example 26.2 in this slide. If the specification had been based on removal ratio, then the basic approach would be the same. The only change would be the specification of the effluent treatment line. Sometimes the effluent treatment cannot be accomplished in a single effluent treatment process. For example, different treatment process might be required to treat contaminant over different concentration ranges. It might also cheaper. This is just a suggestion based on this book. Why so cheaper to use multiple treatment processes rather than a single process? For example, when treating petroleum refinery effluent, it is usually cheap to start the treatment with an API separator and then complete the treatment with other treatment processes such as dissolved effluent depository treatment. So meaning for the removal of the contaminant, the wastewater treatment, normally it's not a single process. So, for example, if the system requires filtration, up to ultrafiltration. So before the ultrafiltration, they need to have several treatment before the wastewater reach ultrafiltration. So some of the example would be before the membrane is population, if needed, is sand filtration, or maybe activated carbon as well before the membrane mucus. Because to maintain the membrane would be expensive. So taking into the same consideration of that. So to have a very quick treatment before the well, separation. Example for petroleum refinery effluent. The API separator is a cheap process to remove part of the contamination before passing the effluent to more expensive treatment processing. So membrane is more expensive compared to population regulation any primary treatment. There's limitation in the performance or the cost associated with effluent treatment process might dictate the requirement for multiple treatment processes. The graphical approach to targeting minimum treatment flow rate can be extended to multiple treatment processes from in figure 26.3. To start with division of mass balance for the multiple treatment processes, then decomposition of the effluent composite curve. We have 2 specification of the individual treatment processes and composite of the effluent stream and treatment. In the first figure, A, the effluent composite curve is divided into part of the effluent mass load being treated by the different processes. MTP1 and MTP2, so TP refer to treatment process. This is for multiple treatment process. The effluent composite curve is then decomposed into two parts at this point of the division with the mass load. So all the arrow goes to the CE, which is the environmental discharge limit. Although the system now has we have two systems. Decomposition is the opposite procedure from creating a composite. In figure 26.43b, the mass balance division is such that the effluent composite curve between CI is for C1 and CA need to be decomposed. In this way, two separate effluent composite curves are created for treatment by treatment process 1 and treatment process 2. Treatment line for TP1 and TP2 are then matched against their respective decomposed effluent composite process in figure 46.43. The matching of the treatment line against the decomposed effluent composite is now the same as the for single treatment process as described. Previously, specification can be based on upward concentration or removal ratio. So for removal ratio, the method for calculating it is different. It's not the same. Figure 26.43d shows that decomposed effluent composite curve and the treatment line combined to obtain composite for each. It should be noted that the treatment line for TP2 in figure 26.43c would actually cross the original effluent composite curve and would appear to be invisible. So if you remember the water, this is water supply line. This line and this line. If you still remember, the water supply line cannot exceed or above the composite curve. Otherwise, the design would be invisible. However, composite of the two treatment line does not cross the original effluent composite curve. The combination of the two treatment line leads to a feasible solution. And finally, the relative contaminant mass load on the two treatment processes can usually be varied within reasonable limit. As load is shifted from TP1 to TP2 and thus beside the relative capital and operating cost will change. This is a degree of convertibility can be optimized. It's just there's no example for multiple treatment. Designed for minimum wastewater treatment flow rate for single container. Having established how to set the target for the minimum treatment, the next question is how to design to achieve the target. At the moment, we have learned about targeting minimum wastewater treatment flow rate for single container. You have two methods. So the fixed object concentration or renewable ratio. So far, covered design for maximum water use for single concentration within the water grid system. Water main. So this is design for minimum wastewater treatment for single containment. Having the design is able to achieve the target based on the starting concentration of the stream relative to the pinch concentration. So still remember, pinch is normally it must be in the middle of the composite curve. So composite curve will be slightly convex. So the point where water supply line touches the composite, the tangent to the composite curve is the pinch point. So for group 1, group 2, group 3, group 1 concentration of stream J in group 1 and group 3 is from C1 equal to group 1 concentration 1 is more than concentration of pinch or above the pinch point. Group 2 concentration 2 is equal to concentration of pinch or the same level of the pinch. Next is below the pinch. So C3 is less than pinch. If the water flow rate above the flow rate below are defined to be the total water flow rate in the concentration interval immediately above and below the pinch concentration specifically. As shown in figure 26.44. So the pinch is here. So above would be above this line. Is below this line. Mandatory. Continue shown in figure 26.44. Then MW both let the flow rate equals equal to MW1 summation of this water flow rate for stream J in group 1 and MW below is equal to water flow rate for stream J in group 1 plus water flow rate for stream J in group 2. So remember, group 1 is above the pinch, group 2 is on the pinch line, similar to pinch. So SI is a total number of stream in group 1. S2 is total number of streams equal to how to know. So any stream with concentration above the pinch will be considered as group 1. Any stream is similar to pinch concentration is group 2. Because the treatment line with fluoride wastewater WT is pinched with the composite curve at this point. The following relation hold. So MW mean is less than MW, it's more than MW above and less than MW below. Which means that for water flow rate for group 1, the sum of the stream is less than wastewater flow rate minimum less than the MW below. This one is refer back to question 26.14 and 26.15. Therefore, the minimum treatment flow rate target, so MW mean is given by, so MW mean equal to MW1 water flow rate for group 1 on the stream plus partial. So theta here refer to 1 to 0, so we need partial of water flow rate for group 2. So not all the stream in group 2, all will be considered, but not all the not the total amount. Question 2618 revealed that the treatment flow rate target can be achieved when all the wastewater stream in group 1 are treated together with some of the wastewater stream from group 2, none from group 3. So some of them, so partial wastewater stream from group 3. Having identified the stream to be treated in order to achieve the flow rate target, it is still necessary to prove that the mean inlet concentration of those streams, C mean in, is equal to the targeted inlet concentration for the treatment process C. So if the treatment flow rate target is the minimum, is what the flow rate consists of the wastewater stream defined by equation 26.18, then the mean inlet concentration of the stream treated mean is given by 26.19. So C mean in equal to water flow rate for group 1 all the stream times concentration for group 1 plus partial of water flow rate for group 2 times pinch, because group 2 is equal, the concentration is equal to the pinch concentration over water flow rate group 1 plus partial water flow rate. So from figure 26.44, the targeted inlet concentration in for the treatment flow rate target is given by So C-in is referred to here, which is the water supply line. C-in equal to C pinch plus delta C. Delta C is C pinch concentration minus C-in, or C-in minus pinch into delta C, where it's equal to C pinch plus delta MT minus delta M pinch, in here referred to flow rate, over minimum water flow rate. So MT is from here to the end of the composite curve. Delta MT, so minus delta M pinch from initial to pinch over MW min. So MW min here can be calculated based on 26.18. Where delta C is the concentration change through the treatment process above the pinch, then knowing that delta MT equal to delta M pinch equal to water flow rate group 1, concentration of group 1 minus concentration of pinch, or concentration of group 2. Delta MT is total mass treatment load. Delta M pinch is mass treatment load below the pinch. Question 26.21 and 26.18 can be substituted into equation 26.20 to give the targeted inlet concentration C-in. So equation 26.21 plus 26.18 is plugged in into 26.20. This is 26.20. So you get 26.22. So here you see C-in equal to C pinch plus. So delta MT minus delta M pinch, you can substitute with the right hand side, plus over MW min. MW min is right hand side as well. So then all of this term you bring it, multiply with C pinch. So you get this elaborated equation over the denominator here. So at the end, C-in is equal to C min in. Equation 26.22 proves that the mean inlet concentration of all the streams that is equal to the stream to the inlet. So mean inlet concentration of all the stream that is equal to targeted inlet concentration. Now you know C-in is equal to C min in. Summarizing the above discussion, give the following design rule, which must be observed to achieve the treatment flow rate target. Design rule 1, if wastewater stream start above the pinch concentration, then all of the flow rate of all of this stream must be treated. So any stream above the pinch concentration, all must be treated. For design rule 2, if wastewater streams start at the pinch concentration, then these streams are partially treated and partially bypass the effluent treatment. This is referred back to the group 1, 2, 3. So design rule 2, if wastewater stream below the pinch, then you may bypass all the stream, bypass the treatment process completely. Design rule 2 is dictated by the mass balance. The amount of the wastewater stream from group 2 to be treated can be calculated from. So how much is the amount of wastewater stream? Because group 2 is partially treated. So MW2, the flow rate for group 2 is equal to delta MP minus MCI, delta MCI over C pinch minus C out. So C out is actually below the equilibrium environmental discharge limit, where delta MCI C1 is equal to water flow rate group 1 C concentration of group 1 minus concentration of E. E is environmental discharge limit. These three basic rules create a segregation policy to ensure that the target is achieved in design. If the effluent treatment involves multiple treatment processes, as shown in figure 26.43, then the same basic approach can be followed as for single treatment processes. The problem is decomposed as shown in figure 26.43b, decomposition of the processes. This provides the target and the basis of the design. Each treatment process has its own pins, and the network design for each can be developed separately. The network design are then simply connected. Example 26.4. Consider again 26.3. The last example is about targeting the minimum wastewater treatment for single container. The target for the three stream in table 26.8 was determined to be 60 ton per hour. So this corresponded both with a treatment process achieving 10 ppm at its outlet, also one with a removal ratio of 95%. Design an effluent treatment network to achieve the target of 60 ton per hour. So 60 ton per hour is based on previous calculation, example 26.3, where The pitch is at 5.4 MC max load. So 5.4 is kilogram per hour divided by ppm times 1000. The ppm is from 100 to 10, which 10 is the fixed outlet concentration. 90, 5400 over 90 is 60 ton per 60 ton per hour. To achieve the target in practice, require that the starting concentration relative to the pinch be first identified. The pinch is at 100 ppm and stream 1 start above the pinch. How do you know? Because the concentration. The pinch here is at 100 ppm. Stream 2 start at the pinch and the stream 3 start below the pinch. The stream 1 must be based on the design rule 1, 2, 3. So design rule 1 states that if wastewater stream start above pinch concentration, then all of the flow rate of all of these streams must be treated. Stream 2 is partially treated based on the design rule. Stream 3 is totally bypass the effluent treatment. The question remains as how much of stream 2 goes through the effluent treatment and how much bypasses. Why? Because stream 2 here is fall under design rule 2, in which the concentration is at pinch. So if the wastewater stream start at the pinch concentration, then this stream are partially treated and partially bypass the effluent treatment. There are method in the shown before how to calculate the amount of wastewater from group 2 to be treated. The question, okay, if stream 1 with a flow rate of 40 ton per hour must go through the effluent treatment, then the target for effluent treatment is 60 ton per hour, then 20 ton per hour from stream 2 must go through the effluent treatment process. So only 20, so 5 ton per hour from stream 2 will be bypass the effluent treatment, meaning it will be mixed with stream 3 here. Why? Because stream 3 is on it is below the pitch, so this stream can bypass the treatment process. Figure 26.45. Figure 26 will show the design structure for the effluent treatment together with the flow rates. So stream 1, we have 40 ton per hour. This one is refer back to table 26.8. Stream 2 is 25 ton per hour, stream 3 is 10 ton per hour. So from 40 ton per hour, stream 2 will be divided two parts. So 20 ton will go to stream 1 So 60 ton per hour goes to the treatment process, while the 5 ton per hour from S2 will be diluted by stream 3 at the end 75 ton per hour. The design to achieve the target is therefore a matter of following 3 simple rules. It is worth highlighting a few points. Firstly, stream starting at the pinch must be partially treated and partially bypassed in order to achieve the target. The splitting of the stream, while it is necessary to solve the problem exposed theoretically, is often not acceptable in practice. It provides design complexity in the need to split the stream. Also, regulatory authorities often find such an arrangement to be unacceptable even though it solves the problem according to their regulation. So meaning, environmental regulation often have requirements for such criteria, such as best practice or best environmental option. It is therefore often considered to be not the best environmental practice to partially treat a stream. If part of the stream needs to be treated, then why not the whole stream? Is the argument. If the partial bypass is eliminated, then all of the flow for the stream starting at the pinch is fed through the treatment process, meaning based on table 26.8, instead of dividing it, 20 goes to the treatment plant, 5 goes to the dilution with the stream 3. Then the performance of the system will exceed that of the regulatory requirement. While this might seem to be a drawback in a small system, in practice it is not such a problem. In practice, rather than dealing with 3 streams, it is likely that the number of streams from a site might be of the order of 100 or more. So, of course, yeah. In situation where 100 or more streams are present, changing perhaps one stream that is at the pinch to fully go through the treatment process rather than partially bypass will have a very small effect on the overall system performance. Another point regarding the design process is the effect of the stream that are already below the environmental. So meaning what we have what I have shared with you is theoretically based on the design rule, the stream at pinch must be partially treated. But in real time, it is possible to treat all the contaminant in stream fall under group 2. In practice, for a large site, many of the stream will already be below the environmental limit. These are dealt with as shown in figure 26.42 in sanctum. They should not be treated by bypass along with all other streams below the pinch. The design for minimum wastewater treatment flow rate, you have three design rules. So before you can design, you need to identify the pinch point. So any stream above the pinch must be treated. Pinch on the pinch. So stream with concentration equal to concentration of pinch must be partially treated, but below the pinch concentration, we can bypass the treatment process completely. So far for targeting the minimum wastewater treatment product for single contaminant based on the pinch point, are required to use 60 ton of per hour of water. So how to reduce it more is to regenerate the wastewater instead of uh, discharge it. The basic principle of regeneration was introduced in figure 26.2. So we have fresh water used in oil operation. And this is for water reuse. Regeneration reuse. For regeneration reuse, you see here the fresh water goes to operation 1, goes to operation 2. So from operation 2, it will be regenerated. Then goes to operation 3. Then goes through wastewater. This is reuse. This is regeneration for recycling. So regeneration for recycling fresh water goes to all the operation 1, 2, 3. Then partial of the wastewater here goes to regeneration and return back to mix with the fresh water inlet. Some of it is fresh. So wastewater. Regeneration is a treatment process but applied with the objective of reusing or recycling the water rather than discharge to the environment. The regeneration of wastewater is most likely to be economic. If it allows processed material to be recovered, it substitutes investment in treatment for discharge by taking up part of the external load as using the overall demand for water. Limits are being imposed on freshwater consumption. So when to consider regeneration is 3 points. Consider the data in table 2610. For 3 water using operation, it is desired to minimize the consumption of fresh water and generation of wastewater. A regeneration process is available with a performance that can achieve an output concentration of 5 ppm. So first stream from 0 to 200 ppm with concentration mass flow rate is 4,000. 4,000, how to calculate this? No. Calculate limiting water flow rate is 4,000 divided by 200. Same to 100 to 50 is from 100 to 450. Start by considering the format of the process for use only. So for use only, you require 60 ton per hour of fresh water. So from here, the target for the data interval to this frequency for use only is this. So we do the composite, limiting composite curve. So the water supply line from 0. So we continue to 1 minute. Let's continue. This is LCC for reuse. When targeting for regeneration, whether regeneration reuse or regeneration recycling, the objective is to divide the water using operation into two groups: those using fresh water and those using regenerated water. The grouping strategy depends on whether it is desirable to include or avoid recycling. Take first the case of regeneration reuse, in which no recycling is allowed. So regeneration reuse is your, as on this figure. So fresh water goes to operation 1, and for operation 2, the water will be regenerated and goes to operation 3. This is a regeneration reuse. Figure 26.47 gives a simple algorithm to provide an initial grouping for problem exploiting regeneration reuse, in which recycling is to be avoided. So here you have two groups. First is requiring water with lower concentration than regeneration can achieve. Second one is can accept inlet concentration greater than regeneration can achieve. Regenerated water. From here, you have more information to balance mustard as evenly as possible below the reuse only page. In figure 26.47, some of the operation that can accept a concentration greater than regeneration can achieve. Also put to fresh water such that the balance of the mass load between fresh water and regeneration water below the reuse pinch in figure 26.46 is as evenly distributed as possible. In this example, from the data given in table 26.10, operation 1 must be fed with fresh water. It is then a matter of deciding whether operation 2 and operation 3 are fed by fresh water or regenerated water. The mass plot below the reuse pinch up. So refer back to figure 26.2. So operation 1, this is for regeneration reuse. Operation 1 is fed with fresh water. Operation 2 also with fresh water. And operation 3 is with regeneration reuse from operation 2. So the method with below the reuse pinch, stream 1 is 4,000, stream 2 is 5,000, stream 3 is 3,000. So 3,000, although in table 2610 here, it's 9,000. Referring back to 26.46, above the pinch, we have 6,000 MC. So 9,000 minus 6,000 is 3,000. That's how they come up with this value. Given that operation 1 belongs to the freshwater group, then an arrangement with operation 1 and 3 in the freshwater group, and operation 2 in the regenerated water group balance the mass load below the reuse pinch as evenly as possible. This arrangement is shown in figure 26.40. In this case, stream 1 will receive 4,000 gram per hour of fresh water. Stream 3 is 3,000 hour of fresh water. And stream 2 will be regenerated for use. The target for the data from table NC content for regeneration reuse expecting a regeneration process with an upload concentration of 5 ppm. The stream being fed by freshwater option 1 are used to construct a limiting composite curve. For these two streams, the target freshwater is 35 ton per hour. Only operation 2 is included in the group using regenerated water, and the target for regenerated water starting at 5 ppm is 25.6 ton per hour. So in this case, although in 26.2, the one is just an example. In this case, stream 1 and stream 3 will be fed with fresh water, and the wastewater regenerated from these two will be regenerated, goes to stream 2, some of it will go to the wastewater. So 35 ton per hour here is calculated by total of freshwater feed for stream 1 and stream 3, which is 7,000, and 7,000 gram per hour is divided by is divided by 200 ppm based on the pinch point. So you get 35 ton. So meaning at this line, the value is 7. Here is 7. How about stream 2, regenerated water? The regenerated water for stream 2 is 5,000 based on table 2610 is 5,000 gram per hour. So based on this figure, it started at 25 ppm. Sorry, 5 ppm. So 5,000 divided by 200 minus 5, you will get to 25.6 ton per hour. So from the 35 ton per hour freshwater, the regenerated is only 25.6, then the rest will go straight to the wastewater. It's the wastewater. Given that the target for wastewater at 25 ton per hour is greater than the target for regenerated water of 25.6 ton per hour, some of the water from the exit of operation 1 and 3 goes directly to effluent. Yes, 9.4. The remainder being regenerated and used in operation 2. While figure 26.47 provide an initial grouping, there is sometimes scope to improve the targets through migration of stream from the freshwater group into the regenerated water group and vice versa. The scope to improve arises from the fact that there are now 2 pinches for the system, the pinch for freshwater and the pinch for regenerated water. In some problem, exploiting the interaction between the pinches allow the target to be improved. There are 3 basic approaches to refine the grouping of a stream by such migration. A conceptual approach based on the freshwater and regeneration pinches. Combinatorial search and mixed integer probabilities. In fact, in this simple example, there is no scope to improve the target by migration, and the final target is not given in figure 26 to 48. Design to achieve the target uses exactly the same water network design as so far, but carried out separately on the 2 groups of streams. The 2 designs are then connected together via a generation process to comply with the outline flow diagram shown on figure 26. This flow diagram. Design for radiation reuse for the problem in figure 26.10 is this one. So fresh water goes to operation 1 and operation 3. Only require 35 ton per hour. You still remember for use only, you are require 60 ton per hour of fresh water. And after but if you choose to regenerate for use, only required 35 ton per hour of a significant reduction, significant saving. So from operation 1, we save 20 ton per hour here, 15 ton fresh water. From operation 1, 15 ton will go and mix with the fresh water. For operation 3, and from operation 3, 25.6 will be regenerated for operation 2, while 4.4 is goes to wastewater. As with regeneration reuse, the objective of regeneration recycling is to divide the water using operation into two groups, those requiring fresh water and those requiring regenerated water. So from figure 26.5, this is for generation for recycling. So divide into two groups requiring water with lower concentration and regeneration can achieve. Fresh water can accept in the concentration greater than regeneration can achieve regenerated water. This is diagram for regeneration recycling. The fresh water goes to all the operation, then regenerated, then recycled. Some goes to wastewater. This time the algorithm is as simple as dividing the stream into those that require water with a lower concentration than regeneration can achieve. And those that can accept a concentration greater than regeneration can achieve. The target based on this initial grouping as shown in figure 26.51. Again, there is sometimes scope to improve the initial target by migration. This again arises from the fact that there are two pinches in the problem, and the interaction between these two pinches can, in some cases, be exploited. So in this case, stream 1 will receive fresh water. So for this is based on 2016 for 20 ton per hour. 20 ton per hour here. Based on this is 4,000, meaning this is 4,000 divided by 200, we get 20 ton per hour. How about regenerated water? So for regenerated water, this refer back to the mass load below the reuse bin. So stream 1 get 4,000 gram per hour. Stream 2 is 5,000 gram per hour. Stream 3 is 3,000 gram per hour. So for regenerated water, this is the water supply line. This is the composite curve. For stream 2 and 3, the pinch is at 200. So the total is 5,000. Total mass load below pinch for stream 2 and 3 is 8,000. 5,000 plus 3,000. Divide by 2 at pinch at 200. Minus 5. We get 41 ton per hour. In contrast to regeneration use, however, the migration will only move stream from regenerated water into fresh water in order to reduce regenerated water costs. This migration can be based on a conceptual approach. combine yourself and mixed integer programming. Once the final target has been accepted, the design is a matter of designing the network for the two groups separately and then joining the two designs together via the generation process in the recycle. The final design to achieve the target, this is for generation recycling. Even in this figure, so in this case, only 20 fresh water. So regeneration use require 35. So for regeneration recycling only require 20 ton per hour. First operation one, then regeneration from here. Okay, where is that? Recycling. Recycling. For recycling is 21. From here, 25 goes to operation 2, 60 to operation 3. 14 ton per hour function 3 goes mixed with 16 and 13. So at the end, 20 water in, 20 water. So for this exercise, a process involves 4 water using operation as detailed in table 26.11. So later you need to know how to construct the composite curve and to target the water flow rate. This is for use only for regeneration. To construct the grid diagram. So what to do first is to construct the limiting water composite curve for this operation. So y-axis is the concentration in ppm. X-axis is the concentration at x-axis is the mass load. So in this case, the water letting flow rate is not the mass load. Mass load is in kilogram per hour. So for this question, you need to calculate the mass load. So for calculating the mass load, the equation is mass load mc over ppm, and concentration delta c is equal to limiting water flow rate. So to find the mass load, you need to multiply limiting water flow rate with delta c. So in this case, 20 times 300 is 6,000. MC here is 6,000. How about limiting water? So mass load for operation 2 is 46 ton per hour times 200. How much? 9,200. So once you calculate MC. Calculate first. So you calculate for all four for all four operation. Identify the MC first. You can download the slide from Philip as well. Just join us. The numbers. Continue with the exercise for this. So I already upload one paper about best cascade analysis. We discuss after this. So anyone needs the system? What to do for this exercise? Want to share your calculation? So you construct the limiting metadata for operation. In this case, what is limiting metadata? That one in the book you can read Robin Smith book, page 595. So what we need to do is draw the arrow bus from 0 to 300. 0 to 300. That one is the y-axis. For the x-axis is 326,000. So MC is in kilogram per hour, so divide by 1,000, 1,006. So for mass load concentration, that one is accumulated. Meaning MC for second operation, I calculated for 9,000. 9,200. Last operation one is 6,000. So 15,200. And so on. Later you will get the limiting water data for the 4 operations. So once you get the limiting water data, you can construct the limiting composite curve. That one you need to combine the arrow into one single line. Once we get the limiting composite curve, look like this. Look like this one. So this is the limiting composite. Once we get the limiting composite curve, we draw the water supply line until it reach the so you stop here. So this point here is the pinch. You can calculate the minimum water flow rate from this pinch. How much I'm not sure. You need to calculate. So once you get the pinch, you target the for water flow rate for reuse. Second question there, B, refer to page 607, the last week, or this last week. So you need to set the target. So either you fix a output concentration or you use a removal ratio. It is for the second question. For the third question, you refer back to 596, also inside the slide. Under design for maximum water reuse from a single contaminant, we start from to design the grid. We start from constructing the water main. So for this case, water main, we have three water main, fresh water main, and pinch water main, and the discharge water main. So discharge here is at 600 ppm. See here the maximum 600. When you draw the stream inside the design grid, this one referred to figure 2618 inside the book will be displayed 597 to so you have four stream. Once you draw the stream, you can identify the C in. Identify the C in. From the C in, you can start to connect the stream. That one is figure 26.19, page 598. Yeah, okay. So the end, the answer would be something like this. Yeah, this is the water network. How many steps? 4 steps for question C. There's no question. But later you need to do the exercise. For how many exercise? You refer to Robbie Smith book. Let's start with the easiest one. Water flow rate for reuse. Okay. Before we start with gas cascade analysis, if you give 10 minutes, you go to elib, you find file 1 here, you read through first. You read through first about optimization and targeting of supply demand of biogas system through gas system cascade analysis framework. This case study is based on farm in Johor. Later we discuss about the gas cascade analysis. For that, just will just then to meet you for 10 minutes, 9 minutes left. Read through first, just read. No need to understand. So continue. Just the system analysis. Oscar. The slide is available in Wikipedia. The biogas decentralized energy system is an important technology in developed countries nowadays. Is one of the energy efficient and eco-friendly technique for production of bioenergy. Besides giving significant impact toward reduction of disposed gas burden and greenhouse gases. Biogas in Indonesia is typically derived from um, anaerobic digestion of biomass. Common biomass feedstock comprises of organic fraction of municipal solid waste, sewage sludge, animal byproduct, as well as palm oil manufactured. In the present situation, the recovery by gas through anaerobic treatment of POME is more predominant in Malaysia, driven by the fifth entry point project of palm oil national key economic area in KEA, which intend to stabilize the oil palm oil in Malaysia. Biogas is centralized energy system. The aim of this article, we just read, is to present a new innovative gas system cascading analysis of Visca based on time-based pitch analysis (TBPA). So far you have seen, you have learned about meeting composite curve, and for gas here, it's about cascade analysis. You still remember we have three methods: LCC, limited composite curve, cascade analysis, and source sink diagram. Vesca is capable of targeting the biogas supply-demand chain, as well as optimal capacity of anaerobic digestion and biogas storage system for a non-total demand profile, with the consideration of energy conversion efficiency for different biogas qualities, charging and discharging of massive end users. For this case, Gesca one of these TBPA, time-based pitch analysis. Design approaches include a supply chain aggregate planning using pitch analysis for meeting the demand over a specific time frame with maximum profit. It was also applied in carbon emission and energy. This is previous example for this car, TBPA, time-based pitch analysis. It was also applied in carbon emission and energy footprint problem management. So in this paper, this is part where they do the literature review for TBPA, because GESCA is based on time-based pitch analysis. TBPA already applied in carbon emission, energy footprint problem, in campus paper, recycling network, water and power system optimization. For power system optimization specifically, TBPA was applied for designing and optimizing an isolated energy system and optimum sizing of hydrogen generator and storage tank. The essence of TBPA is to determine the targeted value, minimum initial and power generator size. This is based on the hydrogen. Based on the time-based energy data via the numerical cascading approach and graphical. For this research, I propose TBPA, known as GESCA, gas system cascade analysis, to target the minimum biogas storage size. Because TBPA here is to determine the previously used to determine the minimum energy storage and power generated, and this author used this method to optimize the biogas project, biogas system, to target the minimum biogas storage size, minimum biogas generation capacity for anaerobic digestion, and biogas charging profile of anaerobic digestion subject to a set of biogas demand profile for different biogas purity level. Methodology. For methodology, you will refer to page 105 of the paper. 1, 2, 3, 4, 5, 6, 7, 8, 9. 12th step. Where is it? Okay, 12 assumption. We have 8 step. Yeah, 8 step for cascade analysis. The cascade analysis for biogas energy system. Oh, okay. We'll include the assumption. So refer to the books, to the paper. There are 12 assumptions. Some of it is the leakage of biogas at compressor is neglected, something like that. Losses during charging and discharging at biogas storage line are negligible, meaning this system is ideal. Yeah, ideal. There is no variation in performance of biogas upgrading or purification unit operation. Excess raw biogas is stored in biogas storage system. Amount of biogas stored at the beginning of the analysis must be equal to the amount of biogas stored at the end of the analysis to ensure stability of biogas storage system. Okay, the first method, the time period is arranged in ascending order in column 1. The time interval of each time slice could be arbitrarily adjusted. So this is for gas. So for water, there are cascade analysis as well, and you need to order it. To arrange it in ascending order, just like this first method. Although the one that you arrange is the flow rate from highest to the from the lowest to the highest. In this case, this is a time-based pinch analysis. The principle is similar, the cascade analysis. This is time-based, so they rearrange the time period, or they call it a time slice. A similar concept. So in this paper, in table 3, page 108, there are 24 time slice. 24 times. Energy equivalent of total raw gas demand, LT, for each time slice T is calculated through a series of steps as follows. Firstly, the energy equivalent of the biogas feedstock with different purity level K, refer to the paper. Purity level K. Fulfilling the energy demand of application Z at each slash T is calculated using equation 1. FPKT. So FPKT is equal to D. D is the energy demand of the calculation. Energy demand of calculation is putting specific example of biogas purity level K. High biogas purity for this one is for energy demand of application Z deploy purity level K D K Z D this one. I'm referring to table 1 in this paper on page 106. The high biogas purity is cooking gas demand and NGV demand. Low biogas purity is electricity demand. Over F apply KZ for West one, the denominator. Conversion factor accounting for energy loss during application. So if you refer back to table 4 inside the paper, FPKT is under demand of NGV. NGV. And okay. So okay. So F denominator is the conversion factor accounting for energy loss during application. D here refer to energy demand of application requiring purity level. Okay. The energy equivalent of raw biogas required for production of biogas feedstock with purity level K, FPO, is calculated using equation Question 2, with energy generation due to upgrading, process being accounted by conversion factor FKU. PGR FKU. FP row. Here is a conversion factor. FK upgrade. So FK upgrade in table 1 is conversion factor accounting for energy change to biogas upgrading system. So the conversion factor become UTT for direct biogas application. FP0 is equal to FPKT over F upgrade. So FK upgrade here. Then The energy equivalent of total raw biogas demand LT is calculated in equation 3. The result are arranged in column 2. LT equal to FP rho. The summation of FP rho is the total gas demand. So the first column of gas system cascade analysis is the time slice. The second column is LT, the total gas demand. So how you calculate LT is from previous equation, from FP rho. So how to calculate FP rho? You need to calculate FP KT. Next, the anaerobic digester capacity, GT, digester capacity, okay, is arbitrarily adjusted and assumed to be constant in each time slice T. This value are arranged accordingly in column 3. So in this case, based on their analysis, the initial anaerobic digestion biogas generation capacity is at 5,400 megajoule per hour. So normally for cascade analysis, when we do the iteration, it normally start with 0. Yeah. Start with 0. Then we can find the negative. That negative will be the new, in this case, the new Q. But for this method that they developed, it started with the initial biogas generation capacity of the process. Net gas energy, NT, I'm referring to table 5, page 109. So 1, 2, 3, 4, yeah, 4, the fourth column. The net gas NT is calculated using equation 4 and arranged accordingly in column 4. So NT is GT minus L LT. So meaning before we can construct the initial iteration of gas car, the data need to be prepared or determined. For FPKT is biogas energy equivalent of the biogas feedstock with different purity level. K is F upgrade is the conversion factor. FPO is the fraction of biogas level with purity level K. So all of this is based on the raw data to calculate. Then you get the LT. This one. Next, the charging and discharging gas energy values are derived from the values in column 4 based on the sign indication. So if net gas demand NT, so when you minus GT minus LT later, so GT here is constant. When you get the value from the current process or start with 0. So in this case, it start with 5,400. So 5,400 minus total gas demand. If the net gas demand NT is positive value, the charging gas energy CT. So CT is the fifth column is calculated using equation 5 and arranged in column 5. This one is for charging energy. For discharging energy is DT. So CT is equal to NT. This is just to differentiate. Oh no, not to categorize it. This is for charging. This column is for discharging. If net gas if net gas demand NT here is a negative value, the discharging gas energy DT is calculated using equation 6 and arranged in column 6. Cumulative gas energy at each time slice. The cumulative gas energy at each time slice T, Qt is calculated using equation 7, and arranged accordingly in column 7. So cumulative is Qt. So cumulative means Qt equal to Qt minus 1 plus Ct plus dt. So refer to table 5 in your paper. This for time slash 1 times slash t equal to 1. The Qt is 2766.63. So the second one is the cumulative, meaning 2766.63 plus charging energy of time slash t. Then you get 6059.94. 6059.94 is for the time slash 2. So time slash 3 is plus time slash 3 because it's a charging. And once you, how about time slash 5? So that one is discharging, so minus 11,073.85 minus 3,709. And you get for time slash 5 is cumulative energy QT of 7364 gigajoule. And so on until time slash 24. It should be noted that the invisible cascading is first conducted assuming zero inventory at the beginning of time period. Okay, yeah, it starts to 0, yes. If you refer, yeah. So for gas cascade analysis, the gas generation is constant, but for the cascade analysis, it must be start with 0. So if you refer to table 5, the last column, new cumulative energy. So Q initial, you can see on top of the first row, Q initial is 0. Then you have times ST 2766 and so on until Q final is 18,291 megajoule. Assuming zero inventory at the beginning of time period to determine the most negative inventory. The most negative inventory doesn't mean it's negative. It could be the smallest amount. In this case, refer back to table 5. Smallest one is 5084 times slice at worth. Yeah, times 2. Second cascading is then conducted with this value. So second cascading, because this is an iteration, you start with 0. Then once you find out the lowest, that lowest value will become the Q initial. This value placed as the initial inventory, pinch time, initial inventory, Q initial, and final inventory, Q final are determined. Better. And refer back, sorry. Then 508 from table 5 will be the second iteration. The percentage change P in the initial and final inventory is calculated using equation 8. So P% equal to Q final minus Q initial. So when you get Q, refer to table 5. Q initial is on the first row. Q final is the last row. Refer to the last column. So Q final minus Q initial over Q initial times 100. If the percentage P is greater than 0.05%, new gas of biogas generation capacity GT, GT new is calculated using equation 9. So for this case, how much? So Q final is 18.91. Refer to table 5. So minus 0. Okay. You need second iteration. Then you can calculate it. So if the percentage of P is greater than 0.05%, new gas of biogas generation capacity, GT new. So GT refer to, okay, so GT gas generation here, 5,400. You need to revise for the second iteration, or for the upcoming iteration. A new gas of biogas generation is calculated using equation 9 distribution, whereby Q final minus Q initial. So in this case, 18,491. Refer back to table 5. Minus Q initial, which is 0. divided by T, total period of analysis 24. So 18491.53 minus 770. Soalnya sorry. 18491, which is the Q final, minus divide by 54 times slice. So 5400, which is the all GT, all gas generation, minus 770. So you have a 4629 this case. So 4629, the new GT. Initial Q is initial, okay. T is okay. The step 3 to 7 are repeated until this P is less than. So once you get the new GT here, you need to calculate to revise the GT here in table 5 for the second iteration. Then calculate back the net gas energy NT, charging and discharging energy CT DT, and cumulative energy QT. So the step 3 to 7 are repeated until the percentage P is less than 0.05%. So table 6 here shows the final JASCA iteration. Not sure how many iterations they do. They said, okay. They didn't inform how many iterations. This is table 4. So table 4 here referred to the raw data. Have a demand of electricity application. The application is demand of electricity, demand of NGV, natural gas vehicle, or demand of cooking gas. Then LT you get from calculating it. So LT is equal to summation of FP for this demand. So we have 3 demands, you know. First iteration of JASCA. We average the time slice in ascending order. Total gas demand is from table 4. So LT equal to summation of zero. So gas generation, this is the initial one, initial value. The initial value is based on the current process area in that farm. The net gas energy, then categorize the net gas energy for charging and discharging. Then you do the cumulative. For charging plus, for discharging minus. Then start with Q initial of 0, we do the new cumulative energy. Based on the analysis, at initial AD biogas generation capacity of 5,400 megajoule per hour, the capacity of biogas storage was determined to be 24,400 32. Whereas the initial and final energy content at biogas storage were determined to be 0 and 18,481 respectively. So the capacity of the biogas here, refer back to table 5, is based on the highest value of cumulative energy. The highest value can refer to time slice 21, 24,431.51. The finding indicated that 18,421, this is the Q final, of energy must be dumped at the end of daily operation cycle to ensure the stability of biogas system. Hence, in order to minimize the wastage of biogas resource via dumping, there would be need to reduce the final energy content to final by reducing the size of gas generation. So at the end, 18,491 here is an excess for the current process. So they conduct cascade analysis to determine the minimum. So that theoretically there is no wastage. From this analysis, two conclusions can be drawn. Firstly, if the final biogas energy content is more than its initial amount, then the AD is oversized. On the other hand, if the final biogas content is less than the initial amount, then the AD is undersized. From the calculation, percentage change P estimate using equation 7. So when you do a percentage change P is after you do the iteration. So if the value is larger than 0.05%, then you need to iterate again. Until the value less than 0.05. The calculation would be repeated to determine the new size, the new size of biogas generation capacity GT. The target of 0.05% was set as a tolerance to ensure the accuracy of the result. This was also to ensure consistent daily energy profile of biogas storage by dumping the biogas before next day without polluting the biogas. So this is the final iteration Pascal with pinch. So they managed to reduce the gas generation up to 4,729 or 4,630 megajoule from the initial 5,400. The pinch occurs at time slice 12. See here, kosong. Once the cascading analysis was completed, the optimal biogas generation capacity of anaerobic digester was found to be 4,630 megajoule per hour, and optimal biogas storage capacity was 16,988. So 16,988 is refer to table 6 is in time slice 21. So similar to time slice, sorry, table 5. Time slice 21 is the has the highest as well. Similar. Selected target initial and final energy content of our gas were found to be integral at 737 megajoule per hour. As highlighted in table 6, the pinch point occur at time slice 12, implying no cumulative energy was stored at biogas storage system at this time interval. This is the composite curve. So figure 8 shows the graphical pinch analysis principle to produce demand supply composite curve based on the graph. The targeted biogas generation capacity for AD was similar to the cascade analysis. The pinch point is at 4,629. So this curve here refer to the composite curve. This is the supply composite curve. In water, this one is the water supply line. And this is the composite curve based on the water flow rate. Because this is a time-based pinch analysis, so this is percent. The y-axis is time. Whereas the targeted biogas storage capacity was 60,900 in 988. Alternatively, graphical analysis can also be applied to perform the targeting of decentralized biogas energy system. Figure 8 shows the figure graphical analysis principle to produce demand supply composite curve based on the graph. The targeted biogas generation capacity for AD was 4629. Inverse gradient of the supply graph. Whereas the targeted biogas storage capacity was 16,988, refer to maximum horizontal difference between demand and supply curve. It showed that initial and final energy content were the same at approximately at 737, and the pinch point occurred at time slice 12, where demand and supply curve touch each other. This is at 737, the supply composite curve. The pinch point is at time slice 12. This implies that the net energy was 0 and no accumulation occurs at biogas storage. The result obtained from the graphical approach were consistent with the numerical approach of GESTA. Okay. We have 13 minutes left. Upon exercise, conduct the gas cascade analysis on the following data with gas generation of 7,000 megajoule. Compare your gas car with the demand supply composite curve. So last semester, the final is gas car. My question, gas system cascade analysis. So the student need, during that time, student need to prepare the table 5 and at least do 2 iteration. So in this case, no need to calculate FP row, FP upgrade, what else? F apply, F application, sorry. Just from total gas demand LP, you need to calculate. You need to calculate GT. In this case, GT is 7,000, not 5,400. This is based on the question. So you start with 7,000 GT, then you calculate for NT. So how to calculate NT? So NT is equal to GT minus LT. So you have the net gas energy there. So from the value, 24 value of net gas energy, you segregate or you categorize it into charging and discharging energy for CT and DT. Then you do cumulative energy QT one by one. After that, you start your iteration using 0 Q initial. So 0 megajoule. You get the Q final. From the Q final later on, this is different. You cannot use the value in table 5 because the GT is different here. So from the final Q final later on, you can calculate you cannot calculate P% because it will be error. 1 divided by 0 is error. So you can calculate the new GT for the second iteration. So for the second iteration, you need to calculate P%. You can calculate P%. So if you have any question, you can try first. Still got time. I think 15 minutes can be done. So for this project, Yaska it is situated at Senai, Johor. I get the data from 2 farm and 2 farm oil mill. So next week we discuss about application as well. Try this. Any question you can check. Uh, what question you could ask? I think catalysis is, I don't know, I prefer catalysis for prints. It's much more economic compared to LCC, 15 compositor. Yeah, that's all. But if you have any question, just contact me or email.
Okay, thanks.